Hello everyone, good to see you here. Come in, take a seat, and welcome to this session on oxygen and water. I'm Emma Cooney from ESRIC and I'll be your chair for this session. We've got a great lineup of speakers, so we'll call to the stage first. Our first speaker, Jack Robinot. Jack is from PROM's CNRS, and he'll be presenting on solar vacuum pyrolysis for lunar oxygen. Welcome, Jack.
Thank you for the short introduction. So I'm Jack Robinot. I'm a PhD student from PROMES, which stands for Process, Materials and Solar Energy. And my work is about solar vacuum pyrolysis for lunar oxygen production. And what I will present to you today is a benchmark of various regolith simulants. So you already had a small introduction on what is pyrolysis by Lucas Bryan at the session before. So the reaction principle is quite simple. So it's a dissociative evaporation. So you have the metals oxide inside the lunar regolith. Then you use the solar energy as a heat source to vaporize and to evaporate the materials. The reaction occurs below the boiling point, and then you can yield some metals and suboxide and some oxygens. And the reaction equation is the Hertz-Newton-Langmuir, which modelizes the flux of evaporation of the oxide. And what I want to show on the plot on the right side is that some oxides are more volatile than the others. So for example, it's a bit a mess, but you can see that sodium oxide, potassium oxide, and iron oxide are much more volatile than the other oxide. And on the bottom of the plot, we have some aluminium oxide and titanium oxide, which are much more less volatiles. And so they require much more longer exposure time to concentrated solar energy to get vaporized. So here is a small flowchart of our experimental setup. So what you can see here, sorry. So here is the pyrolysis reactor. So we have a pyrometer above it. Here is the parabola, which concentrated the solar energy. Under it, there is an heliostat, which tracks the sun, some shutters to control the power, which is supplied to the reactor. Here is a cold finger, which is used to condense some vapor. And there is some argon injection inside the reactor to try to, is it used to measure the oxygen production? And the mix of gases is pumped by a pump, and then it's analyzed and quantified with an O2 analyzer. And then everything is recorded, so the pressure, the temperature, and the oxygen production. And so what you can see here is a picture of the reactor. So you can see here at the focal point of the parabola the sample, the regolith sample. Here the cold finger. Above there is the parabola. So it's a 2-meter wide parabola which can achieve very high concentration, up to 15,000 suns. And so we can reach really high temperature above 2,000 degrees. And here is a filter, and then everything is pumped and characterized. Okay, so the procedure that we are using is quite simple. So we are making regolith pellet. They have a mass of 1 gram. Then the regolith is slowly heated, first at 300 watts of power for 5 minutes, then 600 watts for 5 minutes. And the pressure inside the reactor is at 10 millibar. And we have a flow rate of argon of 0.3 normal liter per minute. And then there is the pyrolysis step, which is occurring during 50 minutes at 10 millibar with the same argon flow rate. And then we'll two products, so the oxygens and some evaporated species, which condense on the reactor wall, on the cold finger, and on the filter, and it's recovered to be later characterized. So this is what look like some typical results that we have been able to obtain with the EAC1 simulant. So you can see the ramp of power, then the O2 which is produced during the pyrolysis. So you can see some some oxygen production. So with this experiment, we did around 1% of oxygen, which is quite modest. We are working toward increasing the yield. And then what you can see here in red is the temperature that has been measured with the pyrometer at the focal point of the parabola. And so the reaction occurred at temperature between around 1,800 degrees. And so the pyrolysis has a duration of around 50 minutes. But at around 30 minutes, we are not yielding anymore that much oxygen. So most of the material that we are able to vaporize has been vaporized after half an hour approximately. And so here is some. Yeah, so this is the result that we have been yielding. So what we did is we compared various regolith simulants. So we have ESA1, BPI, LMS1, and LHS1 and LSP2. So what we found is that we have some similar yield for Mare simulant. So we are able to yield around 10 milligram of oxygen, which is 1% in the mass yield of regolith, which account for 2.5% of the oxygen mass inside the lunar regolith. And we explain that by similar composition, because they are all of three Mare simulant. The LHS1, which is an island simulant, presents intermediate performance with about 7 milligrams of oxygen. And then the lowest performance simulant is the LSP2, which is a lunar South Pole simulant. And it has a performance of about 2.5 milligrams of O2 of oxygen. And then what we tried is to use various minerals that are inside the regolith simulant. And what we observe is that the best performer is the basalt with 12 milligram of oxygen. And the bronzite and ilmenite show similar performance, while the lowest performance is the anorthosite. And so a first conclusion on that is that the oxygen yield seems to be related with the iron content inside the lunar simulant. So the higher the content of iron, the higher the production is. So you can see here in blue it's the simulant, and in red it's the minerals. And you can see a strong relationships between iron content and oxygen yielded. However, there is the relationship is less observable with the minerals. Is really strong only with the regolith simulant. And as said earlier, we yield around 1% of oxygen with the best performance. And so and also there is some point to be underlined, is that on Earth the iron is more oxidized on Earth than on the Moon, sorry. And so that can interfere with the performance of the process. So we don't know yet if the oxidation degrees of the iron can lower the process yield. Then to conclude, and so we screened various minerals, various regolith simulants, various materials, and so we found that the yield appeared to be related to the iron oxide content inside the simulant. However, the yield is still modest. We mostly explain that by the recombination that is occurring in the gas phase. So the metals and the oxygen react together after they are vaporized. And when they condense as oxide. And so the yield remains modest and low because of this phenomenon. And so what we plan for the next is the characterization of the vaporized materials by XRF. And then we are currently building a new solar reactor to operate at lower pressure and to phase out the argon, which remain a consumable. And as lunar processes, we want to avoid any consumable inside the process. And yeah, and that's it. So thank you for your attention. If you have some question.
Thank you very much, Jack. Any questions? Here we are. There's a question. Thanks.
Ainur Yerzhankyzy from the field of FFC electrolysis and laser sintering of regolith. Two questions. One question is, did you have measurements, or you plan any measurements tests about how the melting of the regolith changing, how it absorbs the light, since it's visible light, and as we see, it has a, let's say, shiny effect when it forms the melt. And the second, if you eliminate the argon gas, what is the plan? How will you measure the oxygen later? So if you have a mass spectrometer similar, usually you need, because of the amount of the oxygen gas carrying gas, so it can get pretty challenging.
Yes, thank you for your question. So the first question, it's quite challenging to do some measurement on the emissivity, and there is a lot of stuff that are happening inside the molten regolith. First, like when the regolith is molten, so it became a semi-transparent medium, so we don't exactly know what is happening, and there is some strong difference between the various regolith simulants in their optical properties. So yes, we try to do some measurement, but it's really hard to draw some conclusion because we are not able to do some measurement at high temperature and at molten state. We did some measurement on the glass that we obtained after the pyrolysis and on the regolith. But yeah, and for the second question, so the argon will be phased out from the injection inside the reactor, but the argon will be injected after the reactor, and so we'll still be able to do the oxygen measurement without having argon inside the reactor to lower the operating pressure.
Okay, thank you.
Any other questions? There we go.
Yeah, Florian Hipp from ESRIC. How certain are you about the in situ oxygen measurement, like the amount you generate? And did you see any volatiles inside the oxygen?
No, we are only able to measure the oxygens. So we don't know if there is some volatile. So what we have been observing is that when the experiment is over, there is some vaporized materials. So we guess that there is some volatile inside the oxygen, but we are not able to measure them. We have a mass spectrometer, so we plan also to do some measurement on that to see if we saw some, I don't know, for example, some sulfur or some nitrogen, maybe.
Thanks.
Thanks for your questions, and thank you, Jack, for your presentation. Our next speaker is Alice Dottori from the Politecnico di Milano, and Alice is going to present solid gas carbothermal reduction.
Thank you.
Over to you.
Thanks for the introduction. Okay, so as Emma mentioned, I'm here to present some experimental results on the solid gas carbothermal reduction of lunar regolith that were obtained in the context of the Oracle project, and maybe you heard before during Francesco's talk this morning. Oh, sorry. Okay, thanks. So yeah, the solid gas carbothermal reduction is a two-step process. The first one of them being the actual reduction of regolith with a mixture of hydrogen and methane. And in this step, we produce carbon oxide, mainly CO, that is then converted into water and methane through a methanation step. So the process was demonstrated more than 5 years ago at Politecnico di Milano with just one type of regolith simulants, one highland simulants. And now, in the context of the Oracle project, in preparation for the lunar demonstration, we want to expand our knowledge on the process. So as I mentioned, we flux a mixture of hydrogen and methane in the reactor, in the main reactor. And so we are able to extract carbon oxide, but also part of the methane dissociates, so carbon is deposited on the feedstock, and this prevents the interaction between the solid feedstock and the gases. And to avoid that, and to avoid to stop the process early, we alternate those mixture phases with what we call washing phases, during which we flux just hydrogen, so that the solid carbon has time to react with the feedstock and the hydrogen, and we can clean a bit the feedstock and extend the process duration. Here you can see typical parameters for our test. So the original demonstration was done with 1 kilograms of regolith, and for the lunar demonstration, we aim to work with 50 grams. We have a fixed total flow of hydrogen and methane, and we can vary the inlet fraction of methane. And we tested the process up to 18.5 hours, but for the lunar demonstration, we aim to work within 10 hours long process. As I mentioned, we want to move from a demonstration with one single simulant, that was the NULHT simulant, to more different materials to understand the impact of the feedstock on the process. So we tested other Highland and Maria simulants components such as ilmenite and anorthosite, and also thanks to a collaboration with the University of Padua, we had the opportunity to test also some volcanic soil samples taken from Etna in Sicily. And our main output is the mass of oxygen extracted that we compute through GC measure. In particular, we are interested in the carbon oxide evolution downstream of this main reactor. And once we compute the mass of extracted oxygen, we are also able to define our process yield as the mass of oxygen extracted with respect to the mass of oxygen available in the batch. So these are some of the results with different feedstocks. So as I mentioned before, Highland and Maria simulants, different component. And as you can see, we were able to extract oxygen and to measure carbon oxide downstream of the reactor, no matter the composition of the feedstock. So also with anorthosite and Highland-like material, even if it's really, really low, the production. While for iron-rich materials such as ilmenite and basalts, we can get much higher performances. And also it was interesting to notice that the volcanic soil samples have performance similar to the one of the Highlands simulants, and we expected that from their biochemistry. But those volcanic samples has also an amorphous content that actually did not impact so much the performances in terms of oxygen extraction, but let's say impact more the technical and the operations of the plant, because this glassy part interacts with the wall of the reactor, and so the discharge was really, really difficult. After the process, we characterized the solid feedstock with the SEM and EDX, and we noticed the typical footprint of the process that are kind of glass spheres, silica spheres, that are not present in the virgin simulant. And also we can notice the carbon deposition that we are aware of also from a macroscopic and visual aspect of the material, because it's really darkened after the process, but also we have a confirmation through EDX. And this is a summary of the results. So as I mentioned before, the higher the iron and titanium oxide content in the feedstock, the higher is the process yield. And interesting also, the higher the process yield, the lower is the total content of oxygen, meaning that this less oxygen available is more reactive. And this, let's say, more reactive environment is also confirmed through the estimation of the mass of deposited carbon that we compute with a carbon balance, since we know the sources and the sinks of carbon in terms of methane and carbon oxide. So the highest performing materials, so ilmenite and basalts, has the lower carbon deposition. And to investigate the carbon evolution and to optimize methane exploitation, we also playing a bit with the inlet fraction of methane. Because in the, let's say, in the test I presented before, we were stuck with 15% of methane in the inlet flux. That is our baseline. And we try to decrease this percentage down to 5% and up to 20% to see if we can optimize the exploitation of methane, also because moving from 1 kilogram to 50 grams, we notice a lot of methane downstream of the reaction. So meaning that this methane is just passing by and not interacting. And as we expected, the higher the percentage of methane, the higher is the carbon deposition in the batch. But in terms of oxygen extraction performances, having an, let's say, average values, so 10 to 15% of methane in the inlet flux is still better, even if there's not a strong dependence, but is better in terms of oxygen extraction performances. Also, in this case, we analyzed the feedstock. So after the test, the different reduced material, and our goal was to try to quantify this carbon content, because the values I've shown you before are computed theoretically from the CO, CO2, and methane evolution. So we tried to perform some CHNS analysis, but the results were very different from our theoretical values, meaning that those measurements were really localized and not relevant to test the total carbon evolution. While at the EDX, we found the carbon deposition in all the fragments. So yeah, to conclude, so we demonstrate the process also with different materials with respect to the NuLHT. We were able to extract the oxygen no matter the composition, but we discovered that iron-rich materials have the oxygen extraction yield 1 order of magnitude higher than anorthosite-like. So we are talking 10%, 11% with respect to 1%. So a simple magnetic beneficiation step can improve our process performances, while the carbon evolution still has to be studied to optimize its content. And that's all. If you have any questions.
Thank you very much, Alicia. Are there any questions? Yes, we have a few. We've got time for a couple of questions. How about we start here in the front? Thank you.
Where are you getting your methane for the reaction on the moon?
We are, for the demonstration, we are planning to bring it from Earth. And then the idea is to close the cycle, because after the methanation step, we have methane and hydrogen left. So maybe we can, the idea is to separate them.
But if you have to bring the methane,
yeah,
you might as well bring the oxygen.
Yeah, but the idea is to recycle it. So we
just
bring
wonder
it
if there's
once
enough
and
methane
then,
on the moon to make it worth it. That's
Okay.
just wondering if you'd calculate that.
Well, you don't need to make the methane on the moon to reach orbit. This process recycles the methane. And if we do find a carbon source, then we will make the methane. But since the propellant mass is 75% oxygen in the first place, you can bring methane from Earth and still have regenerators with just the oxygen.
Thanks, Jerry.
Thanks.
Congratulations for the work that you presented to us. If I remember, in the fifth from the end slide, you stated a term, reactive oxygen. Did you?
Yeah?
Yes. You state there that there is also more reactive oxygen. What do you mean by that?
I mean that at the temperature we are working with, so this is around 1100 Celsius, below the melting temperature of the material, we are able to extract the oxygen available in iron and titanium oxide, while the oxygen available in silica oxide, that is, maybe it's this one, it's larger in percentage with respect to the total mass of the feedstock, is more structurally bounded, so it requires higher temperatures. That is in line also moving towards molten carbothermal to extract it.
So you mean that it is reactive, meaning that there are
no, probably reactive is not the
interreactions?
proper
Okay,
word.
thank you.
Thanks.
We're running out of time for questions, but let's just one quick.
Hi, hello, thank you for your work. A couple of questions. You said that you have a methanation step to regenerate the methane, and that happens usually on a catalyst at 250, 300 degrees. So when you are on the moon, how do you plan to cool down your gases from your first step, which is the carbothermal step, to your second step? How do you plan to do it?
For our experience in the lab, we need to reheat the flux. So it's a matter of insulation of proper piping in the plant, maybe exploiting the lunar environment to cool down to the 250 Celsius, not below, because in that case we need to reheat everything. But the fact is that the gases are, we are heating the reactor, not the gases, so the heat exchange is quite fast for what we have seen so far.
Yes, but on Earth you have the atmosphere, so you have the Earth that
it's a
dissolves
matter of
heat.
insulation and of the also the temperature of the lunar payload, but the idea is to exploit also the external environment, so maybe exchange heat.
Okay, thank you.
Okay. Thanks very much, and thank you, Alicia.
Thank you.
Our next presenter is Philipp Reiss. Philipp is from the Technical University of Munich, and today Philipp's presenting his work on the ICE2 thrust project. Over to you, Philipp.
Thank you, Emma. Yeah. Right. Good morning. My name is Philipp Reiss. I'm a professor of lunar and planetary exploration at the Technical University of Munich, and I present on behalf of the whole team at TU Munich. A second chair there is also involved. That's the chair for space mobility and propulsion. So I want to report on the ICE2 thrust project, which is an EU project, and is almost halfway through its project lifetime. And it's very exciting work coming up in the next months or weeks even. So I would like to give a progress report on that. Is it? Can you skip to the next slide? Oops. It's the green one, right? There it works. There you go. So the project we call ICE2 thrust, and I will explain in a minute why we call it this way. It's a project that was started in September 2024. It runs for 3 years, and it's funded by the EU, or the European Innovation Council. It was part of the EIC Pathfinder call, and it's coordinated by the Chair of Space Mobility and Propulsion of the Technical University of Munich. We are not working alone. We have a team of partners as well. The University of Luxembourg is involved, as well as Eurosat as a private entity, and Tektor. So what is the project about? Okay. I don't know, it might be the clicker here, but if you can advance the slides, then I'm happy if you could do that. Okay.
That's the big one.
Yeah, that's pretty clear.
Okay.
All right. So we call it ICE2 thrust because we're looking at the full value chain. Okay. So we're going from ice as a resource or as a raw material to the product that is propulsion for in-space mobility. So we address 3 areas basically here, and let's start from the left. The product side of things is the propulsion, and we generate thrust from water basically using a water electrolysis propulsion unit that is run using solar electric power, so it's a fully sustainable operation here. This would provide in-space mobility, and in order to there's no laser here. In order to provide that propulsion, you need to have refueling as well in space. So one part of the project looks into the proximity operations, the refueling, rendezvous and docking operations to provide that water to the engine. And that's mainly being done by the University of Luxembourg in support of with support of the TU Munich and Eurosat. And then I want to focus on the right part here, because that's what we're doing at my chair, and that is water extraction or ice mining. We are focusing on the moon here to extract water from ice-bearing regolith, and I will tell you more about what the plans here are. So in total, the project is ice to thrust. We want to go from ice-bearing regolith in cold traps, such as these craters in the lunar poles, at the lunar poles, to thrust that is the product for in-space mobility. And from, as far as I'm concerned, this would be the first end-to-end demonstration of this full chain with the product, with propellant as a product. So the idea, of course, hinges on the fact that we have ice deposits in the polar regions of the moon, where it's cold enough so that ice persists near the surface for billions of years. That needs to be proven, of course, so we need to gain more confidence in that. But the general idea is depicted here in this illustration of the Nature magazine, that you would use the very shallowly incoming solar radiation redirected via mirrors that are sitting at on the rims of these craters, redirected into the PSRs, into the dark areas where you would find ice, and then there would be a rover that would collect the evaporating ice and bring it to a storage tank. So we take this idea, the initial concept, and transfer it to the lab, and this is depicted on the right-hand side. We basically have a thermal vacuum environment with a bed of icy regolith. We have a solar simulator sitting on top. We have a mirror system that is steerable as well, so we can control where the beam goes on the regolith bed. It would evaporate then the water there from the icy regolith, and we have a cold trap there as well, which is mobile, which can be retracted. So after collecting ices that evaporate on that cold trap, we can extract it into what we call a liquefaction chamber. And in that chamber, of course, just pressurize the system and collect liquid water. We will then feed this liquid water to another facility, which is just next door in our labs. And that would go into another vacuum chamber with a small engine and an electrolysis cell. And this very water that we have just mined would then go into the electrolysis cell and would be converted to thrust, the end product. So to show you how far we've gotten so far in the project, it has been running for 1.5 years now. I point you to the poster of one of my PhD candidates, Laura Grill. She's sitting in the front row here. She has a poster outside which shows you the hardware that we have been setting up in the lab so far. You see a thermal vacuum chamber. You see on top there's a solar simulator. You see this nice black part here where the sample would sit, so the beam would come from above. The liquefaction chamber on the left-hand side is not yet built because the parts haven't arrived just yet, but it's going to be built in the coming weeks, and we have this steerable mirror, so everything's basically ready to be tested in the coming months, and we basically aim to produce the first results through the remainder of this year. Another poster I would like to point you to is the one of Florian Achon, another PhD student in my team, who's also here. He is looking into the preparation of the sample because, as you know, we don't quite know what to expect on the moon in terms of ice forms of ice, shapes of ice, concentrations, and so on. So we want to investigate a range of different possibilities here. And he's looking into granular ice production, looking into different grinding, blending, methods to produce ice particles of certain sizes and shapes, and we would mix them with regolith to produce certain samples, but we would also look into other methods to really cover a wide range of icy regolith properties. So the main questions we would like to address in this project is, of course, firstly, the basic feasibility of this process. Okay, can we prove this end-to-end demonstration? And interestingly, we will certainly come up with more questions that we went into when starting the project. So this is the research that I'm excited about. We will find out about all these questions, address some, answer some, but reveal a whole bunch of new questions that we will have to address in the coming future to really close gaps and realize this value chain in space. So some questions that I pointed out here are what is the water extraction efficiency? How much water do I get out versus how much power I put in? What is the water capture efficiency? So how much water do I lose along the way when capturing with the cold trap? How is this dependence of the efficiencies on solar power, regolith properties, ice concentrations, also forms of ice and locations of ice, cold trap parameters as well. How is the cold trap positioned with respect to the beam or the site where the water evaporates? That's all very open questions that we need to address. The purity, of course, of the produced water is one of the main questions because the electrolysis cell has quite demanding requirements on the purity or the electric conductivity of the produced water. So we will analyze the produced water between the two steps of extraction and utilization. And then also, of course, with a perspective towards scaling up, we need to investigate the production rate. So while this is a batch process, we want to investigate how can this be transferred to a semi-continuous process to really provide a continuous supply of water for continuous refueling operations. So that are the main questions that we would like to address in the coming months until the end of the project. And I invite you to visit ice2thrust.space and our channels on social media to stay informed about what we're doing. We will regularly publish what we're doing there. And with that, I thank you for your attention.
Thank you so much, Philip. Do we have questions?
ESRIC. So two things. Are you aware of the work that Colorado School of Mines did on this exact kind of process of using a solar lamp to extract volatiles and water and have a cold trap in their chamber?
I'm not so much aware of what has been done at mines. I'm aware of a few other projects that have looked into that.
So they had, I can't remember what the solicitation was, but they basically had a full chamber, exactly what you're talking about. Now their lamp was smaller. What you will find is if there's any water ice in the top layer, it will desiccate, and the poor thermal conductivity of the regolith will prevent you from getting much more. Also, they did come up with what we called the shaved ice approach of shaving granulars of ice and mixing it with regolith in the chamber. So I would suggest, I'll try to find it myself, but definitely look at Colorado School of Mines work that they've done.
Thanks for the hint. Yeah, I'm pretty sure that Florian is aware of the shaved ice approach because he has been looking into that as well. Regarding the desiccated layer that you mentioned, this is exactly what I want to investigate further, because this has been hypothesized as well, and based on modeling you can find this out, but we want to know how does the sublimation front basically migrate through the regolith, and how do we need to apply the heat in an efficient way, really?
Well, the concern is always that once you vaporize the water, it doesn't go upwards, it goes to a colder location just deeper. And exactly, so I think they saw a little bit of that as well.
Yeah.
Hi, thank you for your presentation. I've got two questions. How do you want to cool your cold trap actually, and how much do you think you'll be able to capture per effort or per batch each time?
Right, so the cooling will be done via a direct connection to the the cool shroud or the cool sample bed. We have looked into additional Peltier cooling to just provide an extra delta T. But yeah, we will try it out without that first and then see how far we go. In theory, you wouldn't require a high temperature difference. I think as you release gases and you're in a vacuum, basically the release is on ballistic trajectories. So you just need to capture, you just need to provide a cold surface close enough to where the whole release happens. But this is what we're trying to find out.
Thank you.
Time for one more question. There we go, Kuru.
Kuro Shirogi from NASA. Thanks for the talk. One of the things that you mentioned from electrolysis, right? Obviously, the purification is one of the elements and depends on what electrolysis you use. If you use a proton exchange membrane, the purification of that water needs to be highly pure in order to be, for the naphthalene base or the sulfonic base to be able to handle the electrolysis. Have you considered solid oxide electrolysis? Because they are more forgiving, then they can be more volatiles associated with it as long as it's not solid. So those are the things I think would help to determine how much purification you might have upstream need to have before electrolyze it.
Yeah, absolutely. So as far as I know, it's a PEM electrolysis cell that they're using, but the level of purity that is in our requirements is really high. It's much higher than we would require for potable water. But we will look into also how far you can stretch or relax that requirement, right? So first, because it's an experimental system, you can probably run it in a suboptimal way. But later on, we need, of course, to look into other ways of purification. Currently, that's not the focus of the project, but of course, when we're cold trapping, we can also use freeze distillation procedures later on with either a single cold trap or a staged cold traps. This goes beyond this very project. It's one of the big question marks that we will address, but really, I think we need to explore that much further because purity is certainly an aspect to be investigated further.
Thanks everyone for your questions, and thank you very much, Philipp, for that great presentation. Our next speaker is Ainur Yerzhankyzy from ESRIC, and she will be presenting her work on a water purification prototype. Over to you.
Hello, everyone. Thanks, Emma, for presentation. Today I would like to present our work on development of the water purification prototype for in-situ resource utilization. And this is a joint project between ESRIC and Air Liquide. And also part of this work has been performed under contract with the European Space Agency. So I guess by now all of us know that in 2009, NASA set the bold mission, simply crash spent rockets and answer the question if water really exists on the moon craters. Answer is yes, however, it's not alone, and there are a bunch of other volatiles that could be dangerous. If went untreated, could be dangerous for the astronauts or hazardous for hardware downstream, or some of these elements, such as ammonia or methanol, could be economically viable products. So before we build any purification architecture, taking into account this humid gas mixture, we could take two different routes. First one, we have this raw water feed, and we could selectively remove water from the stream first. And then we could think, what do we do with the collective impurities? Are we going to use them for something, or are we going to just discard those? Or the other option is, based on the impurities in the raw gas stream, what we will do first, are we interested in capturing certain impurity that might have value in the ESRIC chain? And if so, then we have to take another step to purify water, and then what do we do with another collective impurities? So this is everything that we have to consider. And when we think about that architecture, adsorption system could be useful in some of these steps. So some of you that don't know, adsorption is very well-established technology on Earth, and it is used primarily for gas separation and purification. And these columns are filled with adsorbents that selectively adsorb certain gas molecules. And generally, we have 2 columns to imitate the continuous process, because columns are filled with adsorbents that become saturated at some point. On the right side, you can see an image, basically just cartoon showing how adsorbents work. They capture the molecules at higher pressure and cooler temperature, and whenever you reverse the condition, then you will reverse the process. So basically, whatever adsorbents we're holding, they will start releasing. So adsorbents also give flexibility in terms of how you want to regenerate your adsorbents. So today my talk is focused on water purification, but here I wanted to highlight that it's not limited for water purification only. So on the Moon and Mars, it could be used for various applications. Here I'm just listing some. For example, oxygen purification produced from molten salt electrolysis, or it could be used for capturing some of the unused gases from Sabatier conversions or from solid oxide electrolysis cell, just naming a few. So today's talk will show some of our results on simulation. We are using commercially available software, GPROMs. So this is used for process simulating, and we would like to create a digital twin of our hardware. So the idea is to, first of all, build a reliable digital twin and then use it for to speeding up our experimental work, to be able to optimize our hardware, and then predict how it would work on scaling up the system. No? Okay, so before I jump into results, here I just wanted to explain what the breakthrough curve is. Whenever gas comes inside the column, here as an example, humid nitrogen, first of all, we'll sense only nitrogen leaving out of the column, because the zeolites filled inside the column will preferentially adsorb all the water until a certain point when we start sensing the water coming out, and then finally, obviously, the feed concentration will equal the outlet concentration. So any water coming into the system is leaving the column. So at this point, we say that the zeolites are fully saturated and they cannot hold any more water molecules. So with this curve, I just wanted to say that adsorption system could be flexible in a way to decide when you want to stop your adsorption step. Either you want to stop before you start losing any water molecules, or you want to make sure you adsorb as much water as you can, so your column will be mostly filled by water. By doing that, we could play with the purity and recovery of the product. Yep. Okay. Oh no. Back. Oh. I have to go back. Back. Okay, this is good. So, no, one more back. Sorry, one more back. One more slide, please. Back. Oh, okay, here I'm just showing one of our experimental data we did with the pure water in nitrogen as a carrier gas. So our GPROMS model, it will come now. Our GPROMS model was able to predict well the timing of the breakthrough, which is pretty good. However, if you see the blue line, which is the simulation result, it has steeper front, which means that our model still has to be tailored in terms of mass transfer resistance. So this requires still experimental work to be done, and this is work in progress. However, we decided to proceed with the simulation with ammonia as an impurity in the feed. So what we did, we varied the humidity level from 1,500 to 15,000 ppm with 200 ppm of ammonia. We had the fixed temperature of adsorption and regeneration, fixed the adsorbent, zeolite 13X, and we studied how the recovery and the recovery efficiency and the purity will change. So here you see the curve, how the breakthrough curve looks like when you have water and ammonia and nitrogen. So first thing clear is that both of them co-absorb simultaneously until we see the first breakthrough of water coming out. What is the good news is that our simulation predicts that zeolite 13X will favorably absorb water. That's why we see that towards the end, when the column is more or less fully filled with the more or less fully saturated, we see how water pushes out ammonia. And this explains why we have such an overshoot of ammonia concentration. For example, it goes above almost 2,000 ppm, while the feed concentration around 200 ppm of ammonia. So we wanted to study, based on when we stop our adsorption step, how our recovery of water, which is basically extracted water over the feed water sent through the feed stream, then extract efficiency. Why here I distinguish recovery and extraction efficiency, because extraction efficiency is the water extracted over the water captured in the bed. And basically, our regeneration temperature, how much we heat our column, will define how much water we'll be able to release from our zeolites. And then water purity, basically extracted water over extracted water and ammonia from the whole stream. So here, what do we see in terms of recovery? If we stop adsorption step before we see any breakthrough of ammonia and water, then our recovery and extraction more or less settle at the same value, around 85%. And this is basically limited by, it doesn't mean that we're losing water on our outlet, but it is more explains that our 250 degrees of regeneration is limiting full extraction. So basically some of the water that's been captured by zeolites are trapped there. So they will be, when we run the full process, it will be circulating, and not all the volume available on the adsorbents will be available in the next consecutive cycles. So however, when we do the full, when we wait until full breakthrough, then we see that we already lose water, and recovery is around 65%, though the extraction efficiency stays around 85%. In terms of purity, so we observed that we can achieve higher water purity at the end when we have higher water content in the feed, which is kind of logical because we have higher water. But over here, what we were expecting initially, that simulation should have showed us that when we wait until the full breakthrough, we should have higher purity. But this means our GPROM simulation still needs some adjustment, and this is work in progress. And with that, I wanted to say that GPROMs, so far, we observed that it works well in predicting the time of the breakthrough. However, we still need to do more experiments to adjust the mass transfer coefficients, and then have to optimize the purity levels of our product. And what I wanted to highlight again, that adsorption is a versatile process. So if you see this application might be useful in one of your processes, just reach me out. I'll be happy to have a chat.
Thank you, Ainur. Do we have any questions? Oh, yes, we do. Jerry. No. Oh, well, okay. Sorry.
It's a nice talk, very nice talk. I will start my questions from the last slide. You used as a control experiment ammonia.
No, the control experiment was done only with pure water. Currently,
pure water, but you added also ammonia?
That was only simulation.
Just simulation?
Just a simulation. So currently, we are waiting for the hardware arrive, and then...
Okay, well, for the simulation to be accurate, there must be a distinction. Ammonia is a gas, but when it is mixed with water, depending on the pH, becomes ammonium hydroxide or whatever. So it's not a gas anymore. So that is one thing that should be taken into consideration. Another thing is that you are using simulants or regolith, mix them with water, and try to determine what kind of gases there may be released. Is that true?
No, we are not doing that. So what we have is, we consider two things. First is cross data. So we have in-house a setup that will generate a gas mixture. So we have capability to generating gas mixture. Based on the cross data, we can fit this. And the other thing that we will use it is we have alchemist demonstrator. So basically this is the produced water by hydrogen reduction. And then we expect certain impurities in the stream. Again, we're using our hardware. We will imitate and generate this mixture to fit into our system. So yeah, that's how it's going to work.
Okay, but in real life, when you're going to have to extract water out of the regolith, there's going to be mixing of the water with regoliths. And there are going to be a lot of stuff released into the water. It's not going to be only gases, but it's going to be also other very reactive materials, which we know that because the dust is extremely reactive, once it comes in contact with the ice water, these reactive oxygen species will be released on the water. And they are very, very biotoxic. If they are not removed, first of all, of course, they have to be identified. So have you considered this possibility that besides any gases that you are trying to get rid of, you will have also water-soluble reactive oxygen species, for example, hydrogen peroxide. And these have to be taken care of. They have to be neutralized because before the water is going to be used for consumption.
Well, I guess we're here. Maybe I didn't make it clear, but our system works in a gas state only. Is that the point that you're making, that in the liquid, if they are dissolved, then that might be very hazardous?
That's right.
Yeah, but our system is going to work mostly in the only gas phase.
The gas phase is going to be the water, you mean?
Yeah.
Which is going to become out of the regolith.
Yes.
And it would have been first in contact with the regolith. So when then in a second stage, when it becomes gaseous, it will take together other water-soluble stuff, and it will become evaporated also, and will also carry with it the other soluble reactive oxygen species.
Okay. We didn't consider that.
Thanks for your question. We're just running out of time, so maybe if you take it up with Ainur after the session. Thank you.
Oh.
Thank you, Ainur. Next up, we have Dana Lefebvre from the Canadian Space Agency, and Dana's presenting her Aqualuna project.
Good morning, everybody. It's a pleasure to be here at my first Space Resources Week. Today I'll be just discussing the Aqualunar Challenge, why we launched it, how it was designed, and what it's taught us about tackling a problem like water purification on the moon. So I'm sure what will be discussed today will be very familiar to you all, but I hope with the lens of challenge-based innovation, the insights that emerge from it will offer a useful perspective on how we approach complexity, uncertainty as we move towards a sustained presence on the moon. So for this challenge, we started with a commonly accepted presence. Humanity is preparing for a sustained presence on the moon. So once we move beyond short missions, logistics alone are no longer sufficient, and resources must be managed in situ. So that's why water becomes foundational, not just for survival or crew survival, but as a systems enabler for life support, agriculture, oxygen generation, and rocket fuel. So we acknowledged, we also acknowledged that lunar water isn't readily accessible. Based on current knowledge, we know that it's primarily found in the PSR regions and mixed with regolith and volatile contaminants, but we're mindful as prospecting missions continue, we'll refine our understanding, but the challenge was really designed to spur purification technologies that are robust enough to evolve as that data evolves. So with that, we have the overview of the challenge. So the Aqualunar Challenge was launched in January of 2024, where we called on Canadian innovators to develop solutions to purify water on the moon. So what's awesome about challenges is that it's an open call to absolutely everyone. So startups, students, hobbyists, it's not just the usual key players. And the intent was to attract those creative thinkers, not within the space sector as well as not space sector, to solve this unique problem. So we were really fortunate enough to have an international collaboration with UKSA where we ran parallel tracks, and each track was coordinated internationally but run independently, which allowed us to stimulate a wider audience. We also established a distinguished multidisciplinary jury. So we had astronaut, the CSA astronaut David Saint-Jacques as part of our jury, as well as UKSA's reserve astronaut Megan Christian, along with lunar and ISRU experts, water specialists, academics, government, and venture capitalists. So we really wanted these solutions to be assessed through both technical but also mission-relevant lenses. So that brings us to our mission scenario. So this was the hypothetical environment in which the innovators needed to consider when developing their solutions. So the primary objective was to produce at least 1 liter per hour of drinking water that was extracted from the contaminated ice. So innovators needed to take into consideration the environmental hazards, so the fluctuating temperatures, abrasive regolith dust, low gravity, and lack of atmospheric pressure. We also had a feedstock profile mixed with water ice and then several or a range of volatile contaminants. And this composition was inspired by the data from the LCROSS mission. So not as a definitive prediction, but just more so as a stress case that forces purification approaches to handle those chemical and physical uncertainties. So with that, we also had to take into consideration the technical constraints. So systems had to operate autonomously, minimize power consumption, mass and size, solar radiation and windshield, and also be able to survive launch and landing. So it's important to note that meanwhile, we listed all of these requirements, but they weren't necessarily needed in order, not every single innovator needed to meet each requirement, but they just had to kind of take everything into consideration and best be able to produce a solution with those in mind. So with that, here is our stage-based approach. So as you can see, there is 2 distinct tracks, so the UKSA and Canada. For stage 1, we asked innovators to develop a concept design, so focusing on the mission scenario, any assumptions that they have, and then it's really meant to be system-level thinking rather than actual physical hardware at this point. So this really allowed us to cast a wide net and explore a diverse range of solutions. So teams who had a sound approach were then selected by the jury and moved on to stage 2. So stage 2 is where they were able to actually develop those detailed designs and build key components reaching TRL 3. So as you can see, the UK track ends at the end of stage 2, and I'll discuss the winners just in a moment. But I just wanted to take a second to talk about the stage 3, where on the Canadian side, innovators were required to integrate components from their proof of concept into a lab prototype that was actually capable of demonstrating water purification. So we were targeting TRL 4 or higher. Importantly, it wasn't just about funding. So as non-financial support, we offered innovators a wide range of different information sessions, business support, and networking opportunities. One key highlight was hosting the UK and Canadian innovators at the CSA in Montreal for an innovator boot camp where teams had a chance to network and collaborate with each other, participate in expert-led discussions on regolith, commercialization, as well as we were fortunate enough to have David Saint-Jacques talk about his time on the ISS, and then also Megan Christian talk about her time in Antarctica. So notably during the 3rd stage of the Canadian track, as you can see at the bottom here, we had third-party testing of lunar samples that had to be processed through each of the systems to determine the effectiveness in removing those contaminants from their systems. So we also held technology demonstrations where the jury could see their prototypes processing the water samples in real time and produce the samples that needed to be tested. So this stage structure not only was able or the jury was not only able to select winners, but to meaningfully de-risk technologies with potential relevance to future lunar missions. So on the UK track, we had 3 winners. The grand prize winner, Lowland, I won't be able to speak to their technologies in detail, but we saw a wide range of approaches ranging from acoustic advanced oxidation, thermal extraction and distillation, as well as supercritical water oxidations. So these winners were actually announced last year, and it's been great to really see how Lowland from Naker Scientific Limited has done since the challenge. So he's multiplied funding from the initial grant. He's been able to expand his team of 1 person to 4 new employees, and he's also repurposed several components as either standalone components, exporting some, and then sending payloads to space. So here are the stage 3 finalists from the Canadian track. Again, I won't be able to talk about their technologies in detail, but we saw a wide range of technical strategies from electrocatalytic advanced oxidation to integrated thermal and vapor phase processing to systems that deliberately exploit lunar conditions like vacuum and solar energy. So stage 3 was really particularly important because it allowed us, as well as the jury, to move past the theoretical performance and see real hardware responding to those lunar samples. So it definitely helped the jury to be able to make an informed decision, and with that, one solution was ultimately demonstrated the strongest combination of performance, robustness, and scalability. So to announce the grand prize winner of the Canadian track, I'm pleased to play a little video from CSA astronaut and Artemis II crew member Jeremy Hansen.
Hi, I'm Canadian Space Agency astronaut and Artemis II crew member, Colonel Jeremy Hansen. The Artemis campaign's objective is to return humans to the moon, this time to stay. Living and working on the lunar surface is a very ambitious goal that will require bold ideas and new technologies. The Aqua Lunar Challenge was created to develop innovative ways to purify water on the moon, a critical resource for sustaining life as well as producing fuel and food. The grand prize winner of the challenge is Canadian Strategic Missions Corporation. Their concept, LunaPure, is designed to provide a low-maintenance, sustainable water purification process that takes into consideration the challenging conditions of working on the moon. Congratulations to CSMC on your innovative spirit and vision.
So we're fortunate to have CSMC here in the audience and at Space Resources Week. So if they're wearing the nice jackets, I'm sure you've all had a chance to talk to them by now. It's halfway through the conference, but if you want to learn more, yeah, give a wave, there they are. Yeah, give them a round of applause. So congratulations once again, and if you are learning, or if you'd like to learn a bit more about LunaPure, I welcome you to talk to Gustavo and Ian about the technology in a bit more detail. So the benefits of the Aqua Lunar Challenge. In total, we received 54 proposals, and we funded 8 teams to develop their solutions and awarded $1 million in total grant funding. So beyond the individual solutions, we were able to deliver value at the ecosystem level. So not only did we accelerate innovation by giving teams a clear destination tied to a real mission need, we allowed flexibility in how they got there. So we were able to also bridge proven terrestrial capabilities, often developed within other industries, into space-relevant applications, in many cases by non-traditional space actors. So also by engaging startups, researchers, and SMEs new to the space sector, the challenge expanded the ecosystem and surfaced approaches that might not emerge through conventional government funding. So most importantly, we were able to de-risk and mature low TRL technologies within a very short period of time. So this slide really sums up the philosophy of the Aqualunar Challenge by deliberately defining something that feels impossible and then taking a step back. We create space for creativity, risk-taking that traditional programs can't often accommodate. So by rewarding these outcomes, we give innovators the freedom to pursue unconventional paths and combine disciplines in new ways. So initiatives like the Aqualunar Challenge not only accelerate progress toward permanent, sustainable human presence on the moon by maturing those technologies, expanding the ecosystem, and also proving that bold ideas can move beyond concept to credible reality. Sorry, I know I'm over time. I'll just close by saying this, that challenges are a great tool if you're looking to explore new approaches and accelerate progress. So if you're interested in learning a bit more about outcomes-based funding, I'd love to continue the conversation and welcome you to come talk to me.
Thank you very much, Dana. We may have time for one quick question. Otherwise, okay, there we are. Is that Jun? Yeah.
Jun Shimada from JAXA, thanks for your talk. When you issued this challenge to the public, how did you define the concentrations of impurities?
It was through the LCROSS mission. So we used that subset of criteria, or that subset of contaminants, and used that as our percentages of contaminants.
Okay, from LCROSS mission?
Yes.
Right.
Yeah.
Thank you.
Great, thanks very much, Dana. That was a great presentation. Our next presenter is Suzuna Okamoto from JAXA. Suzuna will be presenting development of water extraction systems.
Where's the pointer? Just there. Oh. How can I? Is the later pointer? This one doesn't. Oh, okay. Thank you. So hello everyone, I'm Suzuna Okamoto from JAXA. And today I'm going to talk about the development of water extraction systems using heat transfer fluid for in situ resource utilization. So this research is led by JAXA in cooperation with JGC Corporation. So today I would like to tell these 2 points. First, water extraction experiments from ice-regulus simulant with heat transfer fluid were successfully conducted in Japan this year. And second point is that it has been suggested that the state of lunar water resources may influence the extraction results. So from here, let me explain a little bit of background. And today it is said that ice-regulus is likely to be present in the permanent shadow of the lunar polar regions in the form of ice. So to reduce, sorry, yeah. Sorry, I'm too short. Thank you. Oh, thank you. So to reduce the cost of transportation and to increase the sustainability of space exploration, propellant production using this resource on the moon is being considered. And in our consideration, technical challenges have been prioritized, and water extraction from lunar ice-regulus is regarded as one of the key technologies due to its unprecedentedness and also indispensability. That is to say, water extraction is a technology that has not yet been operated on Earth, and also it is an essential technology for the utilization of lunar water resources. So, in light of the above, we set 2 research purposes. First one is demonstrating a method for separating water from a sample mixture of regulus simulant, water, and volatile additives using heat transfer fluid. And this is because last year we used the microwave, and this year we tried the heat transfer fluid. And the second purpose was investigating the influence of the state of lunar icy regolith on the water extraction. So in order to achieve these purposes, we conducted the experiments. So the concepts of this experiment are to collect water in the icy regolith simulant containing the volatile additives by manipulating the state of water with heat. So first, in the left box, it is the mixture of regolith simulant, water, and volatile additives. And by heating, the volatile components are sublimated. And then the generated vapor goes to the next box, the cold trap, and the ice. The water vapor is converted into ice. And at the same time, the temperature was controlled so that the other volatile additives remain as gaseous state. And so, since the water vapor converted into ice, the pressure drops in the ice in the cold trap, and it works as a driving force for the vapor generated in moving forward to the cold trap. So, as a result, the vapor of volatile additives accumulate in the cold trap, and then at this time the pressure arises, and so those vapors are exhausted into the outer vacuum conditions. And the sample preparation is also an important part of our experiment. There are multiple ways to prepare icy regolith simulant because the exact state of water resources on the moon is still unclear. Nobody knows it. So two methods are deployed to compare, method A and method B. And I will explain the details later, but what is common for both methods was volatile additives. They were mixed for both methods to simulate lunar water resources. And we also refer to the ELCLOS mission. And we saw that the materials in the observed in the ELCLOS missions can be categorized into 3 types. First one is be miscible rather than dissolve as a solute. And second category is dissolved in water mainly as ions. And third one is dissolved without ionization. And after the consideration, we chose methanol and ammonia because they are not present in the atmosphere and thus less susceptible to atmospheric effects. It means that we don't have to put effort to avoid the contamination, just like carbon dioxide. And also, the second reason is that they are difficult to purify and has a big impact on downstream purification equipment. It is the reason why we didn't choose any additives from the category C, because we saw that they are relatively easy to remove after the downstream purification equipment. So this is the method A. Method A is expected to produce icy regolith simulant that is relatively similar to lunar water resources among realistic methods. So the left chart shows how to prepare the samples. First, making the aqueous solution by mixing water and the volatile additives, and at the same time, heating regolith simulant under vacuum environment for more than 6 hours to remove impurities. And then spreading those regolith simulant on the tray and pouring liquid nitrogen to pre-cooling them to minus 150 degrees Celsius. And then spraying the aqueous solution we made on the regolith simulant above the tray. That state is shown on the upper image. We can see some black parts, and they are the regolith simulant coated with icy aqueous solution. And after mixing them, it becomes the uniform state like the image below. And the right image is a state seen through a microscopic lens. Most part, we can see the regular simulant, but we see some blur parts. There, the ice starting to melt. And method B is different for making the ice particles. It was selected to investigate the effect of state of lunar water resources. So we sprayed the aqueous solution onto the liquid nitrogen, and we made small particles like that and that. We made a lot of fine particles and mixing with the regular simulant in the back. So here is the result. So water with the volatile additives was extracted from samples by heating with heat transfer fluid. The extracted water is the right image. And the values are summarized in the table below. The water recovery rates were 78% for method A and 83% for method B. And for the method A sample, only 0.8% of methanol added to the sample was detected in the extracted water after the experiment. And for ammonia, it was only 0.04%. And for the method B sample, methanol, it was 12%, and ammonia, 0.4%. So here, what we can infer from the results. So we successfully knew that the process of extraction was found to purify the additives such as ammonia and methanol, and almost 99% of volatile additives were removed for method A sample, which was expected to be relatively similar to lunar resources. And the difference in the state of lunar water resources has been suggested to have an impact on volatile additives concentration in this extracted water. We can see that the difference reached about 10%. So here is the conclusion. Water with volatile additives was separated from samples of water, additives, and regular simulant frozen mixture in a vacuum environment by heating with heat transfer fluid, and the recovery rate of water reached 78% at minimum. And it has been suggested that the state of lunar water resources may influence the extraction results. So the study will be continued with various parameters to optimize the system. Thank you for listening.
Thank you so much, Suzuna. Do we have questions? Let's go for Jerry.
Jerry Sanders, ESRIC. So what happened to the other additives that were not found in the water that had been collected?
We don't know yet because we haven't added other things at all, but we are planning to add other materials in the future as well.
Well, what I meant was, okay, so you added ammonia and methanol to the water, you put it in the simulants, you heated the regolith and collected the water, which had some methanol and ammonia in it. What happened to the remaining methanol and ammonia? Was it?
Others were exhausted into somewhere else.
Okay,
so
I was
we
just
didn't
wondering
collect.
if you measured that other content to verify that it just didn't coat the walls or something like that.
We have to, but we didn't try it.
Okay.
Yeah.
Thanks. Daniel has a question.
Hi, Daniel Ricardo from Swinburne University. This is a really good talk. I was curious, after you prepared the aqueous solution for the two different methods in terms of the icy regolith, I was curious, did you measure actually how much methanol and ammonia was in the simulant that you made? Because when I've tried spraying liquid water on cold regolith, even though you've got it in a bed of liquid nitrogen, the surface of the regolith is a little bit warmer, and it's really hard to trap all the the liquid that you're trying to spray onto it. So I was curious, in terms of the recovery, have you measured it, like how much you actually prepared versus how much you extracted at the end?
Yeah, thank you for your question. During the experiment, we didn't have any way to measure the ammonia or methanol concentration. So when we measured, it was at the first time and after the water extraction. So we cannot really track the material balances during the experiment, and we are now investigating the way to follow the material balances. Yeah.
There's a question.
Ainur Yerzhankyzy from the field of FFC electrolysis and laser sintering of regolith. My question is about the heat transfer fluid. So for me, it didn't get fully clear, especially in the context of the space, that what will be this system. It will be like a phase-changing liquid between gas and liquid, or solid and liquid. Does it something new, or is it like a conventional system which is already used for heating, cooling applications in space? Is it even scope of the project, the research, or not?
Yeah, thank you for your question. Actually, it was not the scope of our research. We just tried the heat transfer fluid on the terrestrial environment, and we definitely need to check if it can be useful in the space before we are proceeding our project. Yeah.
Thank you all very much for your questions, and thank you, Suzuna.
Thank you.
So that's the end of our session. Thank you all very much for attending. It's lunchtime. Enjoy, and don't forget to vote for the posters.